Alright guys, how are you all doing? Assalamu alaikum. We're talking about KIRCHOFF law. In my first video, I've explained everything you need to understand under KIRCHOFF law. So we need some strategies. How do you move? How do you apply some things in KIRCHOFF law that makes you to understand much more better when you are being given some advanced example. Now, the first thing is that by applying KIRCHOFF law, you used to generate different set of equations. And you see this equation at times to make it much more easier. We usually apply the Gauss-Jordan elimination method at times to solve the Kirchhoff law equation. When it involves like mainly, let's say 3, you get, because you might have multiple equations in order to find different aspects of current, voltage, and the resistor. So what is the logic that is behind this is that you have to label those circuits so that you won't make mistake. So you have to label them. So it helps you in what? Orientation. The second thing is that you have to locate the junction. What is the junction? The process at which the current is flowing. If you had checked my last video, you would have understand what we are saying. Kirchhoff law 1. Now, the junction is also known as like the process at the junction at which the current meets. Either they are coming in or they are going out. That junction. So the second thing is that the junction is where, like we said, 3 or more wire connect. Something like this. So I don't know how to draw very well and I don't have a good idea. So this point here, you can call it a junction. So you have to label a junction also. That is, let's say current 1 is coming in here, current 2 is going through here, current 3 is coming like that. So look at what I'm saying now. You have to label those currents and the direction at which they are coming in and they are going out. Now you have to make sure that whatever you are labeling, you must make sure that there must at least be one current that is going out. Let's assume you have 3 particular currents. There must be at least one of them that will be coming in, then 2 can go out. Or you either have at least one coming in, then 2 can go out. Are you getting what I'm saying? And stuff like that. But there must be surely currents going out and coming in. So that is what they are trying to explain to us here. Now this one says that you have to choose the loops also. I showed you guys that you can have more than 2 certain loops. Talking about the EMF now, like the voltage. So you have to choose the loops in the circuit. And you can know that we have one. You can have one single loop. That one is actually welcome. You can have a single loop or more than a single loop. So you apply the junction rule to it. That's the KCL. What is the rule for the KCL? And you apply the loop rule to solve your question. What is the rule for the KVL? Now, what we have to understand is that we need to understand that resistor and EMF. How do they move? Are you getting what I'm saying? How does it move? Now, if you guys remember, you recall from the last example I did, I said that what? Why the current is moving from a positive potential to a negative potential? It's just like what? Moving from a point A to a point B, the EMF of the battery. So since it's moving from a particular point A to a point B, flowing from first point to like a second point. In that point, the change in the voltage or the EMF would be equals to the first point minus the second point, which will tend to give us a negative voltage. Let me just put it that way. Are you get what I'm saying? So V, this will give us negative IR. Now, from that aspect of view, is that if the battery, that's if the current is moving from a particular high potential, literally moving like this to a low dem, as you can see, high dem to a low dem. Now this is just talking about the resistor. Only the resistor. We have not get to the current itself. If the resistor is moving from a point A to point B, negative. But if it is reverse, you have what? A positive voltage. Are you getting what I'm saying now? This is like a basic thing of what we are trying to break down. This is talking about resistor first. So let's now talk about the EMF. That's like the main current. When it moves from positive straight down, what would happen to the what? To the voltage. And when it moves from negative straight down, what would happen to the voltage? Alright, so as to have a clear intuition of what you are trying to break down, you should know that, like I was saying, you have 2 categories that we are dealing with. With respect to resistor, with respect to EMF, we can say the voltage. Now, when we are moving across a resistor, that's if both the battery supply, the supplier, that let's say the movement of the current in aspect of that, if the current, when moving across resistor, in the same direction as the current is flowing through this point, the direction, that is where the resistor is also moving. That's moving the EMF with respect to where the current is flowing through. Are you get what I'm saying? In that point, you will add the what? The potential drop. You will subtract the potential drop. That is why you are having V, higher V, like the total EMF, higher V minus what? Small v. In this kind of process. Are you getting what I'm saying? So something like that. So that's why you have a negative what? IR. So the next one is that when moving across a resistor in the opposite direction as that of the current, moving opposite direction as that of the current from B to A, like this. In that point, you do what? You add the potential difference. That is why you have a positive what? IR. Now at this point now, we are dealing with what we call voltage source here. So when you are moving across voltage source from a point A, which is negative terminal, how you get what I'm saying? When I'm moving from a particular negative terminal to a positive terminal, you get what I'm saying? When you are moving from what? A negative terminal to a positive what? A positive terminal. I want to try to get something to show you guys something. How you get what I'm saying? Now at that point, when I'm moving from a negative terminal to a positive terminal, as you can see, negative through positive, from negative, starting from negative, over from negative. You are moving from negative, your what? Your voltage would be a positive one. That's the potential drop. Now, if it's moving from positive through negative, are you get what I'm saying? The voltage would be a negative drop. That was why you see in my recent example, why it's just like this direct current is just like we're talking about this man saying that literally we know that a normal dem current moves from a negative potential, but in the aspect of look, we are going to say it moves from positive what? A positive terminal straight to the negative terminal. But in the normal scientific method, for those who understand, it's moving from the negative terminal. But that is not what we are going to talk about for today. So just note this particular thing. It's very, very important to understand them. So the first example I did, for those who don't understand better, this should clear their doubt. Are you get what I'm saying? So we are considering the resistor the other time much more. Let's look at an example. Now let's take a look at something here. This is an example one. And you are being asked to find current 1, current 2, and current 3 that is passing through the particular circuit. Now if you look at, in some questions, when it involves like two loops, at times they might give you directly themselves so that you can know how the movement started. So this is moving, this ABEF shows that the loop moves from A to B, then B to E, then E to F, back to F, and then F back to A. And I guess I've explained something like this in my previous class. The next one tells us that it started from E to B, B to C, C to D, then D back to E. So from the first thing, we should know that we have to look at the junction first. We have just talking about the junction. If you have to look at the junction, you would see that when the current was coming in through here, it splitted into two categories, which splitted into current 3 and current 2. Which means at this very junction now, current 1 is coming in. Are you get what I'm saying? While current 2 is moving out. Now listen attentively. If you look at this point, the way current 2 is coming in, the way current 1 is coming into this point here, current 3 moves out of it, current 2 also moves out of it. Are you get what I'm saying? Because this one is the one coming into the junction. These two are moving away from the junction. So that means that the one coming in would be equal to the total of those ones that are moving out, which is I2 plus I3. That is the junction law. That's the first thing we could discover from the junction rule. Now let's look at, we have two loops there. We can call this the first loop. We can call this the second loop. So let us deal with our voltage now. Now if you look at from the loop, the first loop, let's utilize the strategy I gave you guys. The first law, I told you guys, I talked about resistor and EMF. I said if the current is moving in the same way at which the resistor is also moving, are you get what I'm saying? Not in the opposite direction. In that point, you will be having a negative potential drop, right? So which means that since A to B, the current is also moving in the same direction with it. That means you are going to be having A to B equals to what? A negative potential drop, which will be equals to negative current what? Current I1 and R1. Are you get what I'm saying? So from B to E also the same thing. The current is moving in the same position as that of what? That of the resistor. So at that point B to E, that would be equals to still negative V, which will be equals to negative current 2, resistor 2. So if you look at E to F now, we are not considering resistor anymore. We are considering the voltage there. Are you with me? And I told you guys that from E to F now, that shows that, now think, you have just 3 seconds. From E to F, what are we going to be giving the potential drop? Is it negative V or a positive V? Anyone? E to F. Now, if you have to look at it from a perspective view, you would see that I told you guys in the law, I said if the current is moving from the negative terminal to the positive terminal, and you get what I'm saying, that shows that what the voltage would be what a positive ohm. Let me just show this like this so as to check out one or two things. That would be what? That would be a positive ohm. So since it's moving from the negative straight to the positive, that's E to the F. That will be giving you a positive voltage. And you get what I'm saying? And positive voltage what? Positive voltage 1. Do not forget that. So that is, I guess, from F to EA, nothing is happening now. So it's empty. Now that is for the first loop. Now let's look at the second loop now. The second loop. E, B, C, D, E. That is where it moves from. So from E to B, then B to C, then C to D. How you get what I'm saying? So you would agree with me that the resistor is moving in opposite direction with the current, because E to B shows that it's going like this, while the current is going like this, two opposite direction. So from E to B now, we are considering E to B. So from E to B, that would be equals to what? A positive voltage drop. Are you get what I'm saying? Adding the voltage. So that shows that what? We are going to be having what? I to R to positive. E to B, E is moving like this, the current is going like this, opposite direction. So from B to C, what are you going to still have? B to C. E to B, you have a negative. B to C, what are we going to have at that point? Yes, B to C. You're having I3, R3 now. So from B to C now, we can break it down. Let me even write the loop there. Loop E, B, C, D, E. Are you with me? Then loop A, B, E, F, A. So now, if you are to look at something here now, you would see that you have loop B to C, then C to D, right? And in that case, you would see that literally from loop B to C, what are we going to have? Since the current is moving like this, with respect to the direction, that it becomes negative V, which will be equals to negative I3 R3. Then C to D. What are you going to be having? You know this is B to C, so you can actually write it like this: B to C, then C to D. It's also actually allowed though, but let's just break this down to make it much more clear. Now from there now, C to D. Our C to D would be equals to what now? The same direction, so we have a negative V, and that will be negative I for R4. Are you with me? Then D to E. You can see it is coming from the positive to the negative, which means our D to E would be having negative what? Voltage 2. Are you get what I'm saying? Positive potential to the negative potential. While so D back to E. That is all on our loop. So breaking these two things, these are the two things that we need to understand first and foremost, which we have actually breaking it down. So what do we now need to do next? We need to actually what? Simplify them in order to generate what? Equations. So I'll be wiping this off and using some certain particular sheets to go to them. You can put this down, note it down somewhere. Thank you. Alright, now if you look at this now, from the first loop, we know that we've gotten the current loop, the current law. The current law tells us that what? Current 1, yeah. Current 1 is equals to current 2 plus current 3. That is from the KCL, right? We can call this equation 1. Now let's develop the equation for the loop, the first loop. The KVL, which is the voltage loop, tell us that the sum of all the potential drop with its EMF will be equals to 0. That was what they told us. So from that point now, we should know that when we add up our A to B, what we get the B to E, E to F, everything will be equals to 0 with our EMF now. So from A to B now, you know that will be negative I1 R1 minus negative I2 R2, then plus V1 will be equals to 0. Do not forget that. Now, from our second loop, that one tells us that you have negative 2, you have this from here, it flows with it. Negative, you have E to F, E to B, you have opposite direction. So you have I2, R2, then minus, this moves in the same direction coordinate. So I3, R3, then minus C to D. You have negative I4, R4. So this minus V2 would be equals to 0. Are you get what I'm saying? So from this point now, we could visualize some certain things that we are already leading to different equations to find our current and our stuffs like that. So from this point now, we can simplify this by saying V1 is equals to I1 R1 plus I2 R2, right? Then we can say this one here. Since these are the same thing, we can say you have I2 R2 minus I3 into brackets R3 plus R4. Okay, they're actually not even the same them, but they are, since they have negative value together, you can categorize them as one part. Oh, sorry. Lest I forget. So sorry. There was a little bit mistake. So sorry. Please, this point at which the current is flowing here, it is still that same current that enters into this point here, which means you have current 3 moving through here. You also have current 3 moving through here. So sorry about that. You have current 3 moving through here. You also have current 3 moving through here, which means this is negative I3. The other one was the type. This is I3, not I4. So there's not like no current falling. There's also 3 current. Sorry. So sorry about that. So you have I3 also moving through this point here. I3, I3, I3. So from this point now, you can have negative I3 into brackets resistor 3 plus resistor 4. Negative V2 equals to what? 0. I get what I'm saying. So from that point now, you have this. If you have to find, so we can say V2. Negative V2 is equals to I3 into brackets R3 plus R4, then minus I2 R2. So we need V2. So V2 would be equals to negative I3, then R3 plus R4, then plus I2, then R2. I get what I'm saying. So please, so sorry, note this down. The current does not have any junction, so the current that is flowing through this point will also enter through this point and also even through this particular point. Please, so sorry, note that. Now, you have this. So in the normal term, we can say that we have 3 equations that we need to deal with right now. So let's try to check out 1 or 2 things under it. So while writing this equation now, we can actually break it down to make it much more sensible. So from this point, we can say under this our equation 1, you can say you have I1 minus I2 minus I3 equals to 0. So from here, what is our R2? Our resistor 2, that is 3. So that will be 3 times I1, which will give us 3 I1. So then our this one you have I2, R2 also again. Is it I1 R1? Sorry, why is all this mistake coming up? I1 R1. So that would be R1. You have 3. So 3 I1 plus 3 I2. Are you get what I'm saying? So there's actually nothing in I3. You cannot say plus 0 equals to. Now what is voltage 1? 24. That's 24. So the next one you have I2. R2 is what? R2 is 3. So 3 times I2. That will be. There's nothing in I1. This third one. So you can say 0 plus. Now you have 3 I2. Okay, minus. So minus I3. So R3 plus R4. What is our R3? 3 plus 4. That's 7. So that's minus 7 I3 equals to V2 is 29. So that will be equals to 29. So equation 1, equation 2, equation 3. So at this point, we can apply our Gauss-Jordan elimination method, or you can even use the rule substitution to break it down, and you finally get your answer. I've given some of you, if you haven't checked that out, go to my YouTube page to check that, because that's what we are going to be utilizing to make our work much more easier. Alright, so from this point, we can actually, this is our 3 equation. You have 1, negative 1, negative 1, 3, 3, 0, 0, 3, negative 7. Are you with me? So from that point, we can put it in the matrix form. If you don't know this, go and check out my YouTube channel. I've explained what we call an elementary rule operation there. So at this particular point, you can easily break this down. Now, I might not break it down finish. I'm not using Gauss-Jordan method or anything. I'm just using a normal elementary operation just to find a way to break things down. Alright guys, so at this point, like I said, we need to break down some one or two things, and we apply the row elementary operation just to find a way to just break some things down, then we just apply substitution method. So from this point now, if you have to look at, I want to find a way to make this, now literally on a normal dem, what we usually do is, under Gauss-Jordan method, you find the point whereby all these three would be 1, and at this point you have 0. But me, I'm not doing that way. I just want to find a way to break two things down. Literally maybe getting two equation of it. You get what I'm saying? By removing one single value from either two of them. That's what do I mean by removing. You know, this is 0 now. Let us have another 0 here. Why this one is a normal visible number? I could easily use I1, I2, I1, I2 here to find my current 1, current 2 by using simultaneous equation. So, but since this is 3 is not balanced, I have to find a way to make something balanced. Then from there, I could say under R1, I could say multiply row 1. This R1 is row 1. So I'm performing the operation under row 1. So multiply the row 1 by 3. So I have this as 3, negative 3, negative 3. Then I have 0. Then this, it doesn't affect row 2. It's only row 1 it affects. Then I have 24. So I have this as 0, I have this as 3, I have this as negative 7. Then I have 29. So I'm looking for a point to just break things down. So from this point, I could say that if I'm to subtract row 3 from row 2, I could easily have something like this. So under row, because I want to make this 1 0, I want to make this 1 0. You get what I'm saying? Just to make the equation much more okay. And I can utilize these two bodies here. You can break it down anyhow you like. Anyhow you like. You can use normal method then to break it down. Anyone you like, you feel like. Now, from this point, if you have to look at it, I have this. So under row, let's say under row 2. Let me see, I'm not performing the operation under row 2. I said this times okay, let's say under row 2. Okay, let's say under row 2. Row 3 plus row under row 2 if you have to multiply. So let's say row 2 plus row 1. That's the way I'm moving to, just to make this one looks like 0. So under row 2, I have row 2 plus row 1. Or if you have to say row 3 minus row 2, this will also give me 0. Okay, let's just say under row 2, yeah. Then let's say row 3, row 2 plus row 1. It's still the same thing. So then from here you have 3 plus 3. Let's move on first. 3, negative 3. Then negative 3. I have 0. So 3 plus 3 we have 6. Negative 3 plus 3 you have 0. When you have negative 3, then you have 20. You have 0 plus 24. You have 24. So you write this back normally, you have 0, 3, negative 7, then 29. So at this point now, if you have to look at this, at this particular point, let's assume we can also say row 1 plus row 3 to get what we want. So at this point now, this will be under row 3. So we have to say row 1 plus row 3 just to get what we want. 3 plus 0. So let's write this down back. 3, negative 3, negative 3, and we have 0. Are you with me? So 3, negative 3, we have 0. So at this point, 3, negative 3, negative 3, you have 0. Then 6, 0, negative 3, we have 24. So under row 3, R1 plus R3, 3 plus 0, you have 3. Negative 3 plus 3, that gives us 0. Negative 3 plus negative 7, that will give us negative 4. Are you get what I'm saying? So negative plus negative 7, negative 3 plus negative 7, that will give us negative 10, sorry. So at that point, 0 plus 29, that gives us 29. So at this point, we can actually utilize what we're talking about, which is the substitution method, because this is now I1, I3, I1, I3. Just like you're saying 6I1 minus, this 0 has become useless. Then negative 3I3 equals to 24. Then 3I1 negative 10I3 equals to 29. So from this point, we can break it down to find our equation. Now you get what I'm saying? So So moving on with this, if we are to use elimination method, so we have this as negative 60 I, then plus 30I3 equals to 24 times 10. So this gives us negative 240. So this gives us negative 9I1, this I1, then plus 30I3 equals to 29 times 3. So we have 29 times 3, that gives us 87. Okay, negative 87. So this cancels out this. This gives us negative 69 I1 equals to then we subtract, don't forget, negative times negative you have positive, so 60 minus 60 plus 9, you have 51 I1, then this cancels out. So negative 240 plus what do they call it, plus 87. So you have 240 minus 87. So that gives us negative 153, negative 51 also. Are you with me? So negative cancels out negative, then I1 will be equals to 153 over 51. So that divided by 51, that means our I1 will be equals to 3 ampere. Are you with me? So since our I1 is equals to 3, that is our I1, that will be equals to 3 ampere. So from the point of this now, since we know our I1, we can find our I3 from there. So you can use equation 1. So from equation 1, which is 6I1 minus 3I3 equals to 24. From there, we know what is our I1, that will be 6 into bracket 3 minus 3I3 equals to 24. So 3I3 will be equals to 24 minus 6 times 3 gives us what? 18. So that will be minus 18. Then you have 3I3 being equals to what? That gives us 6. So I3 would be equals to 2 ampere. You get what I'm saying? So I3 will be equals to 2 ampere. Then, if you guys could recall from what we had explained earlier, that current 1 is equals to current 2 plus current 3. Do not forget. How you get what I'm saying? So we know that current 1 is equals to current 2 plus current 3, right? So at this particular point now, oh sorry, there's a little bit typo. So from this point you have negative 3I3. Now from this negative 3I3 you have equals to 24 minus 18. So this will be negative 3I3, negative I3. So your current 3 will be equals to negative 2 ampere. So sorry please. From this point now, using this law, you can get our current 2 directly. You have negative I2 equals to I3, then negative I1. So negative I2 would be equals to, just like what we did the other time, I3 is what? Negative 2, then negative 3. So you have negative I2 being equals to negative 5 ampere, which means I2 will be equals to 5 ampere. So you have to make sure you confirm, because current 1 has to give I2 plus I3. And current 1 is what? 3 ampere. So from that point now, our current 1 will be equals to negative 2 plus what? 5, which will give us what? 3 ampere. Are you guys what I'm saying? So which means that whatever we are explaining here, this is how to find your current 1, current 2, and current 3. So also you might be wondering that what do they call it? Current 3 is negative. Yes, that will be negative, because in respect to the conventional current flow, I think that is from positive to normal. Conventional current is from literally positive, the way we assumed, high potential. But because of current 3 being negative, is that it's moving from the negative electron aspect. So moving from the negative process shows that the current is in the opposite, does that mean saying the opposite direction with respect to the conventional current. So that is why it is negative 2 ampere. So it is correct.